Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to optics and the chapters of lenses and formation of images. This exercise was a previous one in the brevet exams in 2005 first session, first exercise. The title of this exercise is the image given by a converging lens. The aim of this exercise is to study by geometrical construction the variation of the distance lens image as a function of the distance lens object between infinity and the object focus. The document below, they mentioned the document, so now I can use it, represents a converging lens L, its optical axis, its object focus, and a luminous object AB. So here the point F represents the object focus. Then part 1 of this exercise, they are telling me that the object AB is at 6 centimeters from L. Part 1. Reproduce at a real scale the document above on the graph paper. Notice that here the direction of propagation of light is not indicated, but we take it as in the same direction of the positive x-axis, which is from left to right. And whenever we need to reproduce or redraw, we always start by drawing the optical axis at the center, having the same direction of propagation of light, which is from left to right. Then this is x prime and this is x. Then we place the lens L perpendicular to the optical axis at the center using the correct symbol of a converging lens. And we know that the intersection between the optical axis and the lens L is the optical center O. Now the object focus F is located in front of the lens. Two divisions on the optical axis, so 1, 2, this is the position of the object focus F. And the point A is located on the optical axis in front of the lens by 1, 2, 3, 4, 5, 6 divisions away from L. So 1, 2, 3, 4, 5, 6, this is the position of the point object A. And the object B is located one division above A, a hat is found on B. Now let's trace the object AB. Finally, the scale is a real scale, which is 1 centimeter along the x-axis and 1 centimeter along the y-axis. So this is it for number 1. Now in number 2, they are telling me show on the figure with the justification the position of the image focus f prime of L. So whenever we know the position of the object focus, we can directly deduce the position of the image focus because f and f prime are symmetric. With respect to O. So because f is located 2 divisions away from L, therefore f prime will be located 2 divisions also away from L behind the lens. Now in number 3, they are telling me find the focal length of L. Then now we know the position of the image focus and we already have the position of the optical center, therefore we can calculate the focal length by referring to its definition. The focal length is the distance from the optical center to the image focus. So the focal length is equal to the distance from the optical center, which is the point O, to the image focus, which is the point f prime, and we don't forget the bar because this distance may be positive or negative. So f is equal to f prime bar, which is the distance from O to f prime. Notice that this distance is in the same direction of the positive x-axis, so it's positive. And now we count the number of divisions between O and f prime. We have 1, 2. And we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis. This will give us 2. Since the scale is in centimeters, then the value of f will be in centimeters. Then F is equal to 2 centimeters. Always all quantities in physics must have unit. Finally, it's a good habit to write our final answer in a box to make the task easier for the corrector to notice our correct answer. So in this case, the focal length is positive, which verifies that the used lens is a converging lens, because we know that for a converging lens, the focal length is always positive. Now in 4 part A, they are telling me construct with the necessary explanations the image A1, B1 of AB given by L. And the word construct means that we need to trace and justify at the same time. Notice that till this moment, we didn't trace any ray issued from B. Therefore, in order to construct the image A1, B1 of AB, we need to consider 2 incident rays issued from B in which we know how to complete their path. Then we will be able to trace and justify the image. So let me make some space. Now we are in 4 part A. So the first ray that we'll consider is parallel to the optical axis. We know that always incident parallel ray is related to the image focus. Therefore, this ray will emerge passing through the image focus. And we don't forget arrows on light rays that indicate the direction of propagation of light, which is from left to right. This is the tracing of the first ray. Now let's do the justification. An incident ray issued from B parallel to the optical axis emerges passing through the image focus. And the next ray that we'll consider is passing through the optical center. We know that it will emerge without deviation like this. Now this is the tracing of the second ray. Let's do the justification. An incident ray issued from B passing through the optical center emerges without deviation. So now let's trace the image. Always the intersection of the emergent rays is the image. So these are the emergent rays, and this is the intersection point between the emergent rays. So this is the image of which object. Notice that these emergent rays are coming from these incident rays that are coming from the point B. Therefore, their point of intersection will be the image of B. The image here is denoted by B1, so we use the same notation. This is B1. Moreover, a hat is found on B directed away from the optical axis like this. Then we must place a hat on B1 directed away from the optical axis like this. This is the hat. So this is the tracing of B1. Now let's do the justification. Then the image B1 of B is the intersection of the emergent rays. So now we have done the tracing and the justification of B1, and it's left to trace and justify A1. In this case, the point A represents the foot perpendicular of B on the optical axis. Then A1, the image of A, will represent the foot perpendicular of B1 on the optical axis. So this is A1, and now let's trace the image A1, B1. And A1 is the foot perpendicular of B1 on the optical axis. Now in part B they are telling me specify with the justification the nature of A1, B1. Then in other words we need to specify whether the image is real or virtual. We are in for part B. So notice that the object AB is pointing upward and the image A1, B1 is pointing downward, which means that the image and the object are in opposite direction, which means that the image is inverted with respect to the object. And whenever the image is inverted, then it is real. Then let's say since it is inverted with respect to the object AB, then the image A1, B1 is real. One could give another justification why the image is real. Notice the object AB is in front of the lens and the image A1, B1 is behind the lens, and whenever the object and the image are on opposite sides, this means that the image is real. Okay, since the object AB and the image A1, B1 are on opposite sides, then the image A1, B1 is real. Now in part C they are telling me find the distance D1 between L and A1, B1. So this distance D1 represents the distance between the lens and the image. Then distance between L and A1, B1. So D1, which is the distance between the lens and the image A1, B1, consists of 3 divisions. And we multiply by the scale along which you have counted the number of divisions, which is scale along the x-axis. This will give us 3. Since the scale is in centimeters, then the value of D1 will be in centimeters. So D1 is equal to 3 centimeters. Let me write down this value here. So this is it for part 1 of this exercise. Now in part 2 they are telling me the object AB is at 4 centimeters from L. So number 1, construct without explanations on a new diagram the image A2, B2 of AB given by L. So on a new diagram means that we need to construct a new optical system corresponding for the new position of the object, because now the object AB is at 4 centimeters from L. So first let's construct a new optical system. So we will take the direction of propagation of light to be from left to right. Here we are in part 2 number 1. And whenever we need to redraw, we always start by drawing the optical axis at the center, having the same direction of propagation of light, which is from left to right. So this is x prime and this is x. Then we place the lens L perpendicular to the optical axis at the center. And the intersection between the optical axis and the lens L is the optical center O. Because we didn't change the lens, so the position of the object focus and the image focus will not change. So F is located 2 divisions away from L in front of the lens, and F prime is the symmetric of F with respect to O. Now, however, the object AB is at 4 centimeters from L, so the position of the object has been changed. And since, okay, let me place the scale here. So the scale is given by a real scale, which is 1 centimeters along the x-axis and 1 centimeter along the y-axis. So now we need to place the object AB corresponding for the new position. So 4 centimeters, and since we are putting data along the x-axis, so we divide by the scale along which we are putting data. So dividing by 1 centimeter, this will give me 4 divisions. So now the point A is located 4 divisions away from L. So 1, 2, 3, 4. This is the position of A. And because the size of the object didn't change, so B will be located 1 division above A. And now let's trace the object AB. Then now we have constructed a new optical system corresponding for the new position of the object, which is 4 centimeters away from L. And now we are ready to trace the image A to B2 of AB. In order to do so, we need to consider 2 incident rays issued from B. Then the first one that we'll consider is parallel to the optical axis. We know that this ray will emerge passing through the image focus like this. And we don't forget arrows on light rays that indicate the direction of propagation of light, which is from left to right. And the second ray that we'll consider is passing through the optical center. We know that it will emerge without deviation. And always the intersection of the emergent rays is the image of the object. So this is the point of intersection of the emergent rays. So these emergent rays are coming from these incident rays that are coming from the point B. Therefore, their intersectional point will be the image of the object, which is denoted by B2. So this is B2. Notice that a hat is found on B directed away from the optical axis like this. Then we must place a hat on B2 directed away from the optical axis like this. This is the hat. This is the tracing of B2. Now let's trace A2, the image of A. Now here A represents the foot perpendicular of B on the optical axis, then A2 will represent the foot perpendicular of B2 as well on the optical axis. So this is the tracing of A2, B2. Here I repeat that no justification is required, although they told me construct, but in the same part they told me without explanations. This is it for number 1 of part 2. Now in number 2 they are telling me find the distance D2 between L and A2, B2. So in other words, we need to calculate the distance between the lens and the new image A2, B2. Now this distance is denoted by D2, which is the distance between the lens and the image A2, B2, and it consists of 1, 2, 3, 4 divisions. And we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis. This will give us 4. Since the scale is in centimeters, then the value of D2 will be in centimeters. So the value of D2 here is equal to 4 centimeters. And now part 3, which is the conclusion. They are telling me deduce then how does the image distance from L vary as the object approaches F. Now here vary means, by vary they mean we need to indicate whether the image distance from L increases or decreases as the object approaches F. And the word approaches means getting closer. So notice that in the first part of this exercise the object was at 6 centimeters from L, and in the second part the object is at 4 centimeters from L. So which means that the object AB is now closer to the lens. Then let's write down as the object AB approaches F. Now in this case, what happened to the distance between the lens and the image? In the first part, the distance between the lens and the image was 3 centimeters, and when the object is at 4 centimeters from L, the value of D2, which is the new distance between the lens and the new image A2B2, happened to be 4 centimeters. So as you can notice that D2 is larger than D1, which means that the distance between the lens and the image has increased. So this means the distance lens image increases. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.